Hi everyone, our group number is 15 and main content of this project is about the garbage classification based on CNN, which is also called convolutional neural network. The members of our group are Zhou Wen, Xu Wenjie, Wang Qijun, Ye Junqi, and Hou An. Among them, the main work of the first three people is to collect data, image pre-processing, and model building. The work of the later two is model training, model evaluation, and result reasoning. We have cooperated very happily, and each member has invested effort throughout the whole project. First, I will briefly introduce what this project is mainly doing and what it means. Today, garbage classification has become a hot topic in society. With the application and development of deep learning in technology, we have seen the possibility of using AI to automatically sort waste, taking pictures of garbage through a camera, and detecting the type of garbage in the picture. So this project aims to do the garbage classification for the progress of society. As we can see, this project is a classic image classification. For picture problems, the best model in machine learning is CNN. We find the data at the Huawei Cloud Artificial Intelligence Contest. There are about 20,000 garbage images in the dataset. Every image has a related TXT file to describe its label. According to this dataset, we take 40 different types of garbage images as our input data and return the corresponding types of garbage through our model. And due to time and hardware issues, we will use transfer learning in this project at the same time, using the CNN model of the trained VGG16 as our CNN layers, focusing on training our final fully connected layers. In terms of the main tool in this project, we will use TensorFlow.
Part 2 is the data pre-processing. There are about 50,000 garbage images in the dataset. Every image has a related text file to describe its label, and we divide the training set into three parts: 81% for the training set to train our model, 9% for the validation set to verify our model parameters such as enthalpy and batch size variable, and 10% for the test set to test our model and give us the results, which is used only once. And then we do the data analysis. There are 40 classes of images, and the right graph shows the categories distribution. According to the graph, we can see that the number of images as class 3 is much smaller than others, and the number of images as class 11 and 21 is much larger than others. Next, we clean the data. Based on the analysis, we remove some images that have strong noise and reclassify some misclassified images in order to achieve a good trained model. Also, there are certain differences in picture aspect ratios. Therefore, in order to achieve a uniform format of input, simple data transformation operations are performed on the image. In our dataset, we are considering two ways to resize the image to 128 multiply 128 multiply 3. And the first way is to resize the image without padding. In this case, we use the bilinear interpolation algorithm. The bilinear interpolation is performed with linear interpolation, first in one direction and again in the other direction. As a whole, the interpolation is not linear but rather quadratical in the sample location. In this case, the image is scaled with the larger edge as the reference, and the smaller edge is burned to build a square image. And the second way we try is to resize the data that the original image is scaled proportionally, with the largest edge as the reference, and the shortcomings. After resizing the image, some image enhancement operations are used to outstand the features of the image. we may consider the algorithm called the adaptive histogram equalization. The picture shows the comparison of the ordinary histogram equalization and the adaptive histogram equalization. Generally, unlike ordinary histogram equalization, the AHE calculates the local histogram of an image and then redistributes the brightness to change the contrast of the image. Therefore, this algorithm is more suitable for improving the local contrast of images and obtaining more image details.
Part 3 is Introduction of Models. CNN is a kind of feedforward neural network which has excellent performance for large image processing. It consists of three parts: convolutional layer, pooling layer, and a fully collected layer. The convolutional layer can retain the characteristics of the picture. The pooling layer can reduce the dimensionality of the data, and the fully collected layer can output the desired result. CNN has two advantages. Firstly, the local feature extraction of CNN is similar to the feature extraction of human vision, so it can effectively retain the features of the image. Secondly, CNN can effectively reduce the dimensionality of the pictures, which can avoid overfitting. VGG is a deep convolution network for object recognition. VGG has two structures, namely VGG16 and VGG19. VGG16 is a VGG network that consists of 16 layers. This model achieves top 5 test accuracy in ImageNet. We will use VGG16 for the garbage classification. There are three advantages of VGG. First, the structure of VGGNet is very simple. The entire network uses the same size convolution color size and the maximum pooling size. Second, a combination of several small field convolution layers is better than the large field convolution layer. Third, performance can be improved by continuous depending the network structure. Due to the limited hardware, we will perform transfer learning. Transfer learning is a research problem in machine learning that focuses on storing the knowledge gained while solving one problem and applying it to a different but related problem. Let's say that you want to identify horses, but there aren't any public available algorithms that do an adequate job. With transfer learning, you begin with an existing convolutional neural network commonly used for image recognition of other animals, and you tweak it to train with horses, and it will make your horse identification more efficient. So in this project, we will use a pre-trained VGG16 model to help us complete the task of garbage classification.
Okay, in this part I will introduce our main work in this project. After data precision, we will build the convolutional neural network. However, due to the huge number of parameters in VGG16, as well as the limit of the hardware issues, such as memory or GPUs, we can't include VGG16 in our model through the training times. But fortunately, VGG16 in our model is untrainable. Therefore, we firstly input all the resized images into VGG16 and output a feature map whose size is 4x4 by 512 as the input of our afterwards fully connected layers. And then we define 3 fully connected layers and mainly train these 3 layers. For the improvement of our result, we also add batch normalization layer among these fully connected layers to modify the distribution of inputs in each layer. And at the end of the network, we use softmax to output our results. So of course our loss is softmax loss. As for the optimization part, we choose the add-on algorithm to optimize our parameters, which is the fastest one. In the training part for the complexity of our model, we firstly define 4098 units in the first fully connected layer, 2048 units in the second layer, and of course 40 units in the last one, the output layer. During the whole training, we set epoch and batch size in different values and use validation sets to verify our model. Here is part of our results. From the results, we can find that the accuracy of training sets nearly close to 1, but that of validation set is quite low. Definitely our fully connected layers have too many parameters and lead to overfitting problem. Therefore, we multiply the number of units in each layer. We set 1024 units and 512 units in the first two layers, and also try different values in epoch and batch size for variables. Here is part of our results. From the results, we can note that although our model still has overfitting problem, our validation accuracies increase a lot, and the highest one is about 76%. After trying different values in layer units, epoch, and batch size variables, we realized that maybe our bottleneck is our training images and the complexity of VGG16.
Hi, this is Hoan. I will introduce our analysis of misclassification cases and our future works. Okay, first of all, one of the most frequent wrong predictions happened in class 0 and class 18. Class 0 is disposable food box. Most of the images are cubic boxes, but there are some images are round boxes. And the class 18 is plastic ball. Most of the images of class 18 are round balls, so the similarity between the two classes of images features in shape might be the reason of the misclassification. And the other most frequent wrong prediction happened in class 27, class 31, class 32, and class 36. These four classes are glass bottles, splash bottles, wine bottles, and drink bottles. Here are four samples of four classes in the PowerPoint. Actually, we can see that objects in above four images have high similarities in shapes. That's why images of these four classes are misclassified. According to the analysis, the problem of low accuracy may be since the feature extraction is not appropriate enough. In order to solve this problem, we plan to try different feature extraction models as our future work to improve our performance. We have two ideas now. First one is don't froze all layers of VGG16. We can unfreeze top 1 or 2 layers of VGG16 model, train the weights to fit our datasets better. And the second one is try another pre-trained models. For example, we can try the ResNext model, which can apply a split transform merge strategy. Alright, that's all our efforts and works in our project. Our presentation is in the end. Thank you for your attention.